Good morning. Today I'd like to talk a little bit more about the 4 velocity, also the 4 acceleration. We'll look briefly at the 4 momentum again. We'll figure out that photons have zero rest mass. Imagine setting up an inertial frame, which purely for convenience I'll call the O frame here. If I have an individual object which is at rest with respect to this reference frame, let's say that its x coordinate is always 1 and its y coordinate is always 5. When I look at the space-time diagram, the world line of the object is a straight line parallel to the time axis. We have defined the 4 velocity to be the vector that stretches from this point to the same point with its time coordinate increased by 1. If this were calculus 3, this would be the unit tangent vector along the world line. If we figure out the Minkowski dot product of u with itself, we get the strange result that u dot u is -1. If this were Euclidean vector manipulations, that couldn't happen. For a vector to be called a 4 velocity, though, we're going to have to insist that this happens. For a general vector, if I calculate the dot product of vector A with itself, this will be a real number, so that has to be negative, positive, or 0. In the case where it's negative, like for a 4 velocity, we call the vector time-like because in the space-time diagram, the change in position is dominated by the time change. If A dot A is larger than 0, we call that space-like, and if A dot A is exactly 0, we call such a vector a null vector. It's worth mentioning again that in Lorentz transformations from one inertial frame to another, the Minkowski dot product is frame invariant. So if I knew, for instance, that A dot A was negative when using the coordinates of some particular frame, then A dot A would be that same negative number if I used any other coordinates of an inertial frame. Likewise, for space-like vectors and for null vectors. I've made several comments in these discussions about how we do certain things in Calculus 3 that will later cause us grief. This will become especially true when we start looking at gravity, but I can already see it's rearing its head even at this stage. Caution. This 1, 0, 0, 0 may not be that 1, 0, 0, 0. Obviously, I need a little bit of explaining there. Imagine I have some individual who is not at rest with respect to O, and not only that, is not at constant speed and direction of travel with respect to O. The world line of such an individual will not be a straight line in the space-time diagram. It'll be some sort of curve as I've drawn it here. This individual is not at rest with respect to any fixed inertial reference frame, but we've already seen that we can kind of cheat on this. Think of having a point P along the world line. Construct the tangent line at point P. There's a 4 velocity for the material object, a vector that points in the tangential direction, so that the dot product of the vector with itself is -1. Written in coordinates of O, the components of that vector could take on various values, or we could do this. We could say, since this is the tangential direction, I'm going to think of an inertial frame whose time axis is parallel to that tangent line. We've already seen in the past how to construct the entire coordinate system. So there is a frame of reference, an inertial frame of reference, in which right at point P, the individual is at rest. This is a momentarily co-moving reference frame. The time basis vector will be the 4 velocity. And since the individual is momentarily at rest with respect to the momentarily co-moving reference frame, we know what the components of that 4 velocity are. If I were in Calc 3, or if I hadn't been paying attention to everything we've been saying, I would write this. Okay, E0, the 4 velocity, the basis vector number 0 of the momentarily co-moving reference frame, equals 1, 0, 0, 0. If I write that, I have made a deadly mistake. The reason for that is this: since the object is accelerating, its direction in the space-time diagram, its path not being a straight line, the direction isn't constant. So here at point P, the individual cooks up a momentarily co-moving reference frame. Its time basis element points that way. Later on, at some other point of the world line, the person is momentarily at rest with respect to some inertial frame. The tangential direction gives the direction of the time axis. It gives also the direction of the time basis vector. This red line and this blue line don't point in the same direction. Even so, in the momentarily co-moving reference frame at Q, the components of the time basis vector are 1, 0, 0, 0. But this 1, 0, 0, 0 and that 1, 0, 0, 0 are not the same. The first time I came to this realization, it really, really bothered me until I figured out that the problem was actually the solution of the problem also. What we should have said is the 4 velocity at point P is equal to the time basis vector at point P, and now all ambiguity is removed. Here we should have said the 4 velocity at point Q is the time basis vector in the momentarily co-moving reference frame at point Q. Once you see that, there's no problem. If you don't see this, you'll think that this is a constant and its derivative with respect to something must be 0, but that's not true. So I'd like to state 2 sentences before I go on and do more calculational type stuff. Sentence number 1, if I'm thinking about these momentarily co-moving reference frames, if there is acceleration, then the basis vectors are not constant. We've just seen that. More ominously, gravity causes acceleration. There are many words that I could tack on to the end of that sentence, but I'm not going to. I just want to let this stew around in the back of your mind for a minute. If you're thinking of momentarily co-moving reference frames, though, gravity causes acceleration, and if there's acceleration, the vectors that form the basis of these momentarily co-moving reference frames are not constants. Things that are not constants have non-zero derivatives. That's all I'm going to say about that at the moment. One of the ways we talked about the four velocity was to state that is the derivative of the space-time position vector with respect to proper time of the individual or object that we're looking at. If I ignore the difference between 4 dimensions and 3, and the difference between proper time and coordinate time, this would just be the usual velocity vector. Therefore, we're going to make up an acceleration vector. It'll be the derivative of the velocity vector, the 4 velocity in this case. It'll be helpful to make an observation here. U dot U is always -1. It's a 4 velocity. The derivative with respect to any variable, in particular proper time, of U dot U must be 0, because that's what the derivative of a constant, the constant -1 is. Now, I haven't proven this, but it's not difficult to see. The usual kind of product rule works for the Minkowski dot product. So the derivative of U dot U is the first vector dot product with the derivative of U plus the derivative of U dot product with the second vector, U. Also, I haven't proven this either, but it's easy to see that the dot product is commutative. So this being 0 says that that's being 0. If U is the 4 velocity, then I can guarantee you that the Minkowski dot product of U with the 4 acceleration is 0. This is always true. To foreshadow something that's an argument that we're going to use many times, this is a scalar equation. The dot product is frame invariant. If the dot product is 0 when calculated using the coordinates of one inertial frame, then it's 0 when using any coordinates of any inertial frame. I've already done the derivatives here. So what I'm going to do is I'm going to adopt a very convenient frame of reference. At some particular point P along the world line, I'm going to evaluate this equation. I'm going to evaluate it using the coordinates of a momentarily co-moving reference frame at that point. Now here's the place where people get confused. They look at these numbers and say they're constants. So the derivatives of any one of these numbers would be 0. Therefore, du d tau must be 0. But that's wrong. When I write this, I'm only telling you half of the story. This being true means that u, at the point we're interested in, is 1 times the time basis vector at the point we're interested in, plus 0 times the first space component vector, 0, 0. As I move along the path, the basis vectors change. So it is not clear at all that du d tau is the 0 vector. In fact, generally speaking, it isn't. So I'll just make up letters to represent the components of the 4 acceleration at the point of interest using the coordinates of the momentarily co-moving reference frame. I'll call these components Z, A, B, and C. The choice of the letter Z might seem strange, but it won't in a minute. At point of interest, I want to calculate u dot du d tau. This is a frame invariant quantity. I could use any coordinates I felt like to calculate this dot product, and I would get the same answer. So I don't say u dot for acceleration and then an arrow with momentarily co-moving reference frame written above it. This quantity doesn't depend on which reference frame you're using. So instead, we say equals. I have to take the components of the eta matrix, multiply corresponding components together, add up the result, and see what I get. This is true at the given point, no matter which inertial frame I decide to do my calculations with. But u dot du d tau is 0. U dot du d tau is negative z. Negative z must be 0. Z must be 0. As measured in the momentarily co-moving reference frame, the components of the acceleration are A, B, and C in the last 3 slots, and a 0 in the first slot. This argument could be repeated for any point along the world line. So at each point, you can construct a momentarily co-moving reference frame. At the point of interest, the velocity with respect to that frame will look like that, and the acceleration will look like that, regardless of the details. One last thing for today. The momentum is the rest mass multiplied by the velocity. If I form the dot product of P with itself and rearrange the algebra a little bit, since I know that u dot u is negative 1, this ends up being m squared is the negative of the dot product of the momentum with itself. So if you just tell me the momentum as a vector in special relativity, you have automatically told me the rest mass also. But wait, it gets worse. If I have a photon that starts at the origin and travels to the right, at t equals 0, x will be 0. At t equal 1, x will be 1, because the speed of light is 1 in our units. This path makes a 45-degree angle with respect to the time axis. Any transfer of energy or momentum from one point to another caused by this photon has to occur in this direction. So the momentum, which I'm not looking at too carefully right now, must be parallel to the vector that starts at the origin and ends up there. P dot P, though, works out to be 0. The direction of a light ray is always represented by a null vector that says m squared is the negative of 0. The rest mass of the photon is 0. Also, a technicality, there is a vector that points along the direction of the path of the photon, but I can't rig it up so that the dot product of that tangent vector with itself is negative 1 because of this 0 here. So many people will say that photons have no velocity, which technically speaking is true, because u dot u would have to equal negative 1. Other people interpret that statement to mean the path of a photon doesn't have any tangential direction, but that's wrong. There's a tangential direction. So it's kind of a piece of technical language, but our takeaway lesson right now is the rest mass of the photon is zero. If you think about it, it had to be that way. The speed of light in an inertial reference frame in a vacuum is constant. There is no inertial frame in which the photon is at rest. There is no way to get a rest mass out of that. This has gone on longer than I meant it to go on. Actually, this is the second or third shot I've taken at this. It keeps getting longer and longer, so I've made what I hope is an abbreviated, reasonably coherent discussion. In the next video, we're going to pursue this acceleration idea. In the meantime, I hope that everybody has a good day, and I'll talk to you again soon.